So we've seen in other videos how to take a square root of a perfect square or a cube root of a perfect cube. But what if you want to take the square root of something that's not a perfect square or a cube root of something that's not a perfect cube? That's what we'll explore in this video. We'll do it by what I like to call splitting radicals. We'll see what that means shortly. First though, I want to make a little note here. We're going to assume that any variables represent positive numbers so that when we take even roots, we don't have to worry about using absolute value bars to indicate that our answers are positive. So even roots with the radical symbol should always give positive answers, and if you don't assume the variables are positive, then you have to include these absolute value bars in your answer to indicate that the answer is positive. So when we get to the examples in this video, we will assume the variables represent positive numbers to make life a lot easier. And this is a common thing that textbooks will do as well. So you'll see that in a little bit. So the first thing we'll do as far as this new concept goes of simplifying roots of non-perfect powers is we'll start by saying that roots split and combine nicely with multiplication and division. Okay, that's pretty important. What I mean by that is, let's say I've got two things multiplied, like a times b, or just ab, and I've got that under some root, like an nth root. Well, I can split this radical into two nth roots, a and b. So I've got an nth root of a and an nth root of b, and I've still got my multiplication. So that's what I mean by this. Going this direction is called splitting the radical. If I go the other way, if I take my two nth roots and multiply them, well then, since it's multiplication, I could also combine those two radicals into a single nth root where a times b is multiplied underneath that nth root. That direction would obviously be combining, because I have two roots combined into one. I can also do the same thing with division. So if I have an nth root of something divided by, like a divided by b, then I can split that into two radicals, the nth root of a divided by the nth root of b. So that is the split direction for division. We won't really see the division examples in this video, but if I'm talking about multiplication, I might as well talk about division as well. And similarly, if I have two nth roots divided, then I can combine those into a single nth root because it's division. And multiplication and division work nicely with radicals. Okay? Now, they don't work nicely with addition or subtraction. So if I have an nth root of a plus b, that is not, this means not equals the nth root of a plus the nth root of b. So it doesn't work for addition. And that's the biggest mistake I see with radicals, using properties for multiplication and division with the addition, and it doesn't work, okay, with addition or subtraction, in fact. So let me write that. It doesn't work for addition or subtraction. Something else to notice over here when it does work with multiplication or division is the root is the same. Okay, so if this is a square root, the square root of a times b, then this would be a square root of a times the square root of b. So make sure to take note of that as well. So I'm going to put this in a box here just because it's that important, really. That's the property that we'll be using to do the examples throughout this entire video. Now, I mentioned examples. Let's talk about how to do them, and then we'll do some. All right? So now let's get down to the business of how we actually simplify roots of non-perfect powers. To simplify a root of a non-perfect power, we try to separate out the largest perfect power, perfect square, perfect cube, perfect fourth, whatever, that we can, and we try to separate it using multiplication, because we know multiplication works nicely when splitting radicals. Okay, so that's how we do it. Let me underline this. It's rather important. That's the technique we'll be using. So let's do some examples now, and I'll leave the technique we're using at the very top of our screen so we can see it. So here's some examples. Simplify, and like I said at the beginning of the video, we will assume variables represent positive numbers. Okay, that's going to let us not worry about the fact that even roots have to give positive answers. By default, they'll all be positive since the variables will represent positive numbers. All right, so example 1. If I have a square root of 50x to the 7th, 50's, none of this is a perfect square. Okay, so that's what I mean. I'm taking a square root of a non-perfect square. My goal is to take this radical, split it into two radicals, and I'm going to do it using multiplication. Okay, and what goes inside these two radicals have to multiply to equal 50x to the 7th, because my second step is equal to my first step. All right, so how do we do that? What do we go about doing? Well, we try to separate the largest perfect power that we can. Okay, so what we're going to do is come over to the side here and make a list of our perfect squares, because I'm dealing with square roots. So I want to separate out the biggest perfect square, and it has to multiply by something else. So our goal is whatever goes into this first radical is going to be our perfect square piece. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64. 64 is already bigger than 50, so I'm not going to use it. So now I start working. I look at the biggest number and I ask, can I multiply 49 by something to get 50? Well, the answer is no, not using whole numbers. I can't multiply 36 by something to get 50, but I can multiply 25 by something to get 50, so I'll put my 25 here. 25 is a perfect square that goes into 50. Then I need to look at x to the 7th. So I come back to my list of perfect squares and I make my list of x perfect squares, my variable perfect squares. X squared is x squared. X squared squared is x to the 4th. X cubed squared is x to the 6th. X to the 4th squared is x to the 8th. Well, x to the 8th is already too big. I can't multiply it by something to get x to the 7th. So I back up. X to the 6th, can I multiply it by something to get x to the 7th? The answer is yes. So what I'm missing now is the stuff that goes over here, because the two things under the radicals have to multiply to equal 50x to the 7th. Well, 25 times 2 is the 50, and x to the 6th times x to the 1st, or just x, is x to the 7th. And so now my second step is truly equal to my first step, because all this multiplies together to be 50x to the 7th. So I've split my radical using multiplication. What this allows us to do now is my perfect square piece. I know how to take a square root of a perfect square. The square root of 25x to the 6th is 5x to the 3rd. So now I've simplified this. I've taken something that didn't have any perfect squares, I created it, and I took the square root. So I've got 5x to the 3rd with no square root times the square root of 2x. If you want to put a dot for your multiplication, you can. It's not necessary. And that's my answer. Now, if I weren't assuming the variables were positive, I'd have to put absolute values around this. But since I know x has to be a positive number, I know that the answer to this even root is positive. Okay, so that's our first example, and there's a square root. Common mistake here is to put a square root over the 5x cubed, and that's wrong because, sorry about that, that's wrong because the square root of 25x to the 6th is just 5x cubed. Okay, so you're always creating a perfect square so that you can take the square root of it. The square root of 2x is not a perfect square, so we can't take the square root of it. We just have to leave it alone. All right, let's try another one. Example 2, the cube root of 192 x to the 9th y to the 22nd. This is not a perfect cube, so that means I have to split it into a perfect cube and something else that's not, and I split it using multiplication. So I'm trying to get perfect cube under here, under my first radical. So I go off to the side and I make my list of perfect cubes. So I'm looking at 192 first. How can I split that? So I've got 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, and 6 cubed is too big. So now I work backwards. I want to pick the biggest one that works. 125 can't be multiplied by something to get 192, so I can't use it. 64 can be, so 64 goes over here. I'm going to do this one a little differently because you might like it better. I'll put my 64 here, but I know that in my second step everything has to multiply together to be 192. Well, 64 times 3 is 192, so I'll go ahead and put my 3 over here under my non-perfect cube radical. So you could think about it that way. These are my non-perfect cubes. Okay? Alright, now I need to look at my variables, and I'll use x, but it also applies to any variable. So x cubed is x cubed, x to the second cubed is x to the 6th, x to the third cubed is x to the 9th, x to the 4th cubed is x to the 12th, and if you recall now, these are all multiples of 3. So that means x to the 9th, this entire piece, is a perfect cube. So I put all of my x's under my perfect cube radical, and no x's under my other one, because I've got all my x's taken care of. Now I have to look at y to the 22nd. 22 is not divisible by 3. It's not on my perfect cubes list over here. But if I look at y to the 21st, it is, because 21 is divisible by 3. And if I put y to the 21st under my perfect cube radical, and I need y to the 22nd total, then I put y to the first, or just y, under my second radical. And now I can see that this radical symbol is a little bit longer than I need, so I'll erase some. Finally, I created a perfect cube under a cube root. Why did I do that? I did it so I could take the cube root and get rid of that radical symbol. So the cube root of 64x to the 9th y to the 21st is 4x to the 3rd y to the 7th. And all I'm left with is the cube root of 3y being multiplied by it. And that is my answer when I simplify this cube root. I think that's enough examples to get the point across. You're separating out your perfect powers from your non-perfect powers, and then you take the root of the perfect power piece, and that's it. You do it through the use of multiplication.